Hello BC Calculus class, this is Mr. McAllen, and I just wanted to talk to you guys about some of the homework problems and give you a tutorial on how to get through some of them, just in case the solution manual didn't really help. So here we go. In number 27, the problem wants us to generate the first four non-zero terms of the Taylor series generated by this function, the square root of 1 plus x. Now if this was a function that was on our chart, we could just use that Maclaurin table, but since it isn't, we're going to have to generate it from scratch. So what I'm going to do is I'm going to pause the video, I'm going to write up the first four derivatives, and well, actually I'll start writing up now, and then I'll pause it and I'll finish writing them. So the first one is just the square root of 1 plus x. The next one, the derivative, I would consider this to be 1 plus x to the 1/2 power, and then the derivative should follow nice and easy. And the next derivative and the third derivative. Now the reason why I'm only going to 3 derivatives is because the function only requires 3 non-zero terms. So I'm trusting that these terms won't disappear when I plug in 0, and they'll be there. So I have to put them into the polynomial. So the polynomial is going to be, remember, it's the sum of the nth derivative at 0, x to the n all over n factorial. So I'm going to just write that out. The first derivative, or the first term, would be, oh, well, let me do this first. F of 0 is equal to 1. The derivative at 0 is equal to 1/2. The second derivative at 0 is equal to negative 1/4. And the third derivative at 0 is equal to 3/8. So I'm going to use those as coefficients to help me out, or not coefficients, but as like the f term. So when I write this out, I have the first derivative at 0, x to the 0 over 0 factorial, plus the first derivative at 0, x to the first over 1 factorial, and so on until I get to the fourth term, which is, I'm sorry, the third term, the third derivative, and so on. When I write the terms out, I'm going to get 1 x to the 0 over 0 factorial, which is in fact 1. The next term will be, the first derivative will be 1/2. It'll be x to the first power over 1 factorial, which will simplify to give me 1/2 of x. The next term will be the second derivative, which will be negative 1/4. X squared over 2 factorial. And so my next term down here simplified will be x squared over 8. And my last term will be 3/8. X cubed over 3 factorial, which will end up being x cubed over 16. So that's how we find our first polynomial. I'm going to call that, because they said, now this is an interesting thing about the notation, f of x will always be equal to the square root of 1 plus x. But our polynomial, I'm going to label that as p of x, because that's an approximating polynomial, and p stands for polynomial. And they want us now to find, and that is approximately equal to the square root of 1 plus x. So, remember that if we plug this into the calculator and we graph it, and we plug the polynomial into the graphing calculator and graph it, we should see that they look similar, but they may not be exactly equal. Not until we add more and more terms. So now we're going to do part B. Part B says to use the results, this polynomial, to generate an approximation for that. Well, in this case, we're going to kind of pretend that this was something on the table. So I'll just write out the square root of 1 plus x is approximately equal to 1 plus x over 2 minus x squared over 8 plus x cubed over 16. So now when they ask me to find the next function, which is 1 plus x squared, and they're calling that equal to g of x, and this is going to be another polynomial that is approximately equal to, what I have to do is plug in x squared everywhere I saw an x. And it's just that easy. And the last part of the homework, oh, and I might want to simplify this, so I'll just simplify it. We'll go back up to the problem. So the last part is, okay, so that's approximately equal to 1 plus x squared. And the last part of the problem said, I'm just going to cut and paste this down below so we can see it. It said to find the first 4 terms of a Taylor series for this function, but they said h prime of x is equal to what we just found, 1 plus x squared. They want us to find h of x. So what's the process to go from the derivative back to the function? From the first part of calculus, we should definitely be saying anti-differentiating, and we can anti-differentiate the series. And don't forget the c. So what we're going to do is we're going to take our series, which we had, remember, 1 plus x squared is approximately equal to 1 plus x squared over 2 plus, minus x cubed over x to the 4th over 8 plus x to the 6th over 16, and we're going to anti-differentiate that. So h of x, if this is h prime, h will be approximately equal to x plus x cubed over 6 plus, minus x to the 5th over 40 plus x to the 7th over 112 plus a constant. And how do we find that constant? Using the initial condition. They said h of 0 is equal to 5. So I'm going to set that equal to 0. Set that equal to 5, and when I plug 0 into each term, you'll notice that c results in being equal to 5. And we now have our final polynomial for h. And that's equal to x plus x cubed over 6 minus x to the 5th over 40. And they only asked for the first 4 terms. When I put the 5 in there, I'm going to leave off the last term, which is at x to the 7th over 112. I hope this video has been helpful. And what I'm going to do, I'm going to pause, but I'm going to plot both functions. I'm going to plot the g of x function, which is the square root of 1 plus x squared, and I'm going to plot the polynomial. And I want to see and show you how both of them compare when we plot them on the same graph. So after that, I'll conclude the video, but I'll be right back after I plot these 2 functions. And here is the final function. This one here is the square root of 1 plus x squared, and this is the curve fit, which is the polynomial p of x. And as you can see, it matches really nice in here, and it doesn't match so nice outside of 1.5, but as we add more terms, the fit will get better and better. So that's the trade-off. We need more and more terms to match the function better and better, and some functions match with less terms, but basically whenever you try to fit a polynomial to another function, you need a certain number of terms to maintain a certain level of accuracy. Hopefully this video has helped, and I look forward to seeing you in class.